Well, thank you again for the invitation. So I will be giving a two-part talk with Neil Turek, who will come after me. And my goal is really to set up the cosmological picture that he'll then talk about. He'll present a new argument for how to compute the entropy of a cosmological spacetime and how it favors flat, homogeneous, and isotropic models. I want to give some background about why that cosmological picture that he'll be using is interesting, how we began to think about it, and what the advantages are. So this will be based on these 5 papers from the first 2 from a few years ago, which are introducing the idea of the CPT-symmetric universe and how it gives a nice model for dark matter. That was how we originally got interested in it. And then the final 3 preprints here from the past several months provide new evidence for this picture that I'll try to describe toward the end of the talk. Okay, so to introduce the idea, here's a cartoon picture of our universe. The idea is time is running up the slide here, and we're living at the top of the page. We're living at the top of this cone as the universe expands. And with our telescopes, we can look back along the cone to almost all the way back to the tip of the cone, which would be the Big Bang, but we can't see all the way back, but we see close, depending on how you quantify it. We see back either a few 100,000 years after the Big Bang, or more indirectly, all the way back to a fraction of a second after the Bang. And what we see down there at the bottom is a universe that is as simple as you could imagine. It's almost maximally symmetric at first order, and then there are tiny perturbations around that symmetry of a part in 100,000, but they're perfectly Gaussian, perfectly so-called adiabatic, and they have a power spectrum that appears to be a perfect power law, and almost a nearly scale invariant power law. So it's clearly some very important hint about how the universe began, that when we look back toward the Big Bang, things seem to get simpler and simpler. Now, the question is, what is that hint trying to tell us? The traditional picture is that simplicity is a bit of an illusion. The idea is that actually there was an even earlier epoch, according to inflation, where there was a big mess, and then a period of accelerated expansion cleaned up the mess to produce the apparent simplicity that we see. So that's one perspective, but it's important to keep in mind that earlier mess is we have no observational or theoretical evidence that it was really there, and so the whole problem of cleaning it up that inflation does may be a sort of solving a fictitious problem. So here we want to try to take a different, more direct approach. Take the observations at face value. The observations seem to be saying that the universe is getting simpler as we get close to the Big Bang. Let's try to imagine that for some reason that really is the case and see where that leads us. Well, let's first conformally rescale the spacetime to make the Big Bang, the structure of the Big Bang clearer. Then if we really take this early simplicity seriously, the metric close to the Big Bang was just the flat metric eta mu nu times a conformal factor, and the Big Bang is just a momentary zero in that conformal factor where it passes through zero. But it does so as simply as you could imagine. The scale factor a as the function of the conformal time tau has a simple zero, a simple analytic zero proportional to tau. So we can analytically continue that space-time, analytically extend it through the Big Bang unambiguously. And what we end up with is this doubled space-time with 2 sheets. And the first thing we notice is that when we look at the doubled space-time, it has a new symmetry where the time goes to minus t, tau goes to minus tau, is a new isometry of the spacetime. And as a consequence, there's a preferred vacuum state for the scalar field, for any quantum fields that live on the spacetime, the CPT-symmetric vacuum. And what we want to imagine is that really the quantum fields are in that CPT-symmetric vacuum. We're going to imagine that the universe does not spontaneously violate CPT. So what you can do then is take the CPT-symmetric mode functions, which I've called psi 0, and write them as a linear combination of the late time positive and negative frequency mode functions, which I've called psi plus and psi plus c, with Bogle-Lyubov coefficients alpha and beta here. And then you can do that analytically, and then with the formula in the middle of the slide, you can calculate how much of these particles, if the universe is really in the CPT-symmetric state, which I've called 0 sub 0, how much, according to us, the late time observer, how many particles are emerging from the Big Bang? What's the expectation value of our number operator if the universe is really in the CPT-symmetric state? Well, it's just proportional to the square of this Bogle-Lyubov coefficient beta in the middle. And you can work out exactly what that is given by. The details are not so important. But so the point is that there's an effect very much like Hawking radiation. Oh, was there a question? Oh. Should I keep going or?
Yeah, keep going. There's no question.
Okay.
But I have a small question. What is this small h here? H. The small h. What is the meaning of this small h? I understand that p is momenta, x is distance, but what is h?
H is the helicity. I'm working with a spinner, and so the H is the helicity of the field along the momentum p, basically whether the spin points along p or not.
I see. Okay, thanks.
So yes, to do things quickly, I'm not giving very much of the detail, but the bottom line is there's a calculation very much analogous to Hawking radiation, where you in Hawking radiation, the black hole is in one state, but the distant observer defines a different vacuum state, and so according to them, there seems to be a flux of particles emerging from the black hole. Very analogously here, the universe is in one state, we hypothesize, namely the CPT-symmetric state, but the observer far from the bang, long after the bang, namely us, defines a different vacuum state, and so we interpret there as being a flux of particles emerging from the early universe into the late universe. So now I want to use that effect to give an elegant explanation for the dark matter. So here I've listed all the particles in the standard model, and to make a long story short, there's only one conceivable dark matter candidate left in the standard model, which is one of the three right-handed neutrinos. That's the only particle that could still be stable, but we haven't directly observed it yet. And so, in fact, one of those three dark matter particles, we can make it stable by imposing an extra symmetry. Nu right goes to minus nu right in the Lagrangian, in the standard model Lagrangian. And that turns out to also decouple it from the rest of the standard model, making it a perfect dark matter candidate, if we can produce enough of it. Well, by this Hawking radiation-like effect, we can produce it, because, but just using the calculation on the previous page, we can calculate this dimensionless ratio, the number. Yes? Is there a question?
No, go ahead. There's no question.
Oh, there's a ratio of this dimensionless ratio of the number density of dark matter to the this ratio of the number density to the entropy of radiation turns out to be proportional to the dark matter density over M Planck to the 3 halves. And so you can work out that in order that if the mass of the dark matter is 4.8 times 10 to the HeV, then you get exactly the right amount of dark matter to match the observed density of dark matter in the universe today. So in other words, we interpret the observed density of dark matter today in our CPT-symmetric model as a measurement of the mass of this one stable right-handed neutrino. So there's several predictions, testable predictions that this picture makes. One is that the lightest of the 3 light neutrinos is exactly massless. So these are the 3 light neutrinos that we can observe. And yes? Oh. Okay. Is that better? Yes, I believe I've closed the test rooms. Okay. So this can be tested. Upcoming measurements of large-scale structure will test whether the lightest neutrino is really massless. Upcoming measurements of neutrinoless double beta decay will eventually test it as well. A second prediction is that the dark matter should be extremely cold. So other alternative models like warm dark matter and fuzzy dark matter, if those turn out to be right, then our theory is wrong. And finally, we predict that there should be no long wavelength primordial gravitational waves. So if long wavelength primordial gravitational waves are detected, our theory is also wrong. So it makes some falsifiable predictions. So now I want to quickly explain that, introduce the idea that the more extended model that Neil will be calculating the entropy of. So far I've been talking about analytically extending the space-time back through the Big Bang, but now let's also add what we know about the future, namely that there seems to be a positive cosmological constant in our universe. Here is the Friedmann equation for a universe that has both radiation and a positive cosmological constant and some spatial curvature, as a Friedmann-Robertson-Walker spacetime can have. So you can solve analytically, and the analytic solution is given by this Jacobi elliptic function Sn, which is this beautiful doubly periodic function, analytic function in the complex plane. And on the lower right-hand side, I've drawn a picture of what the space-time diagram looks like. It's a kind of 2-sheeted cylinder where, as I go up the outer sheet of the cylinder, the scale factor grows from 0 at the Big Bang to infinity at the future boundary of space-time over the course of a finite conformal time eta. But then as I come back down the inside of the cylinder, it goes back from minus infinity down to 0, and through the Big Bang again, and then back up the outside of the cylinder. The inner and outer cylinders are now again related by a symmetry as I hop from a point on the inside cylinder to the outside cylinder, the scale factor just flips sign. And again, we want to interpret that symmetry as not just an artifact, but as a real hint about the universe, and make use of it. One bit of evidence that we should take this analytically extended spacetime seriously is that, in brief, what I try to explain here is that if I look in the complex conformal time plane, the solution has all sorts of poles, and those poles end up the fact that when I try to compute the physical time, I have to integrate the scale factor times the conformal time eta, and the integral depends on how I go around the poles, introduces a ambiguity in the imaginary time direction in the proper time, which corresponds to the space-time being at a finite temperature, which is exactly the usual de Sitter temperature, but now computed for a much more general space-time. Another thing one can do is put matter on the space-time. And if I put matter on the space-time and I ask that it respects the symmetry, which I want to take seriously, the symmetry which exchanges the inner and outer sheets, I find that symmetry forces the matter fields to obey a reflecting mirror-like boundary condition at the bottom end of the space-time, at the Big Bang, but not at the top end of the space-time, because the matter solutions turn out to be analytic at the bottom end, but they have an essential singularity up at the top end of the space-time, at the future boundary. So that means that the universe, just as a consequence of symmetry and analyticity, the matter fields in our universe seem to obey a very restrictive boundary condition at the past boundary, at the Big Bang, but no corresponding boundary condition at the future boundary. And we think that gives a simple new explanation for the observed arrow of time, the fact which ordinarily doesn't have an explanation, that the universe's entropy seems to be growing as we get further away from the Big Bang. We say that is because the fields satisfied a very restrictive boundary condition in the past, but no such boundary condition in the future. It turns out that this same reflecting boundary condition in the yes? Okay, thank you. It turns out this same reflecting boundary condition in the past forces the primordial perturbations to have a number of restrictions which actually agree with observations. So it forces the primordial vector perturbations or vorticity perturbations to vanish, which is good because we don't observe those. It forces the decaying mode scalar perturbations to vanish, which is good because that agrees with observations of the cosmic microwave background that the scalar modes were all synchronized so that they oscillate at the same time in the same phase. And it also rules out the decaying mode primordial gravitational waves, tensor perturbations, but that's in any case, we already saw that there were no primordial tensor perturbations according to us. And then finally, in the final minute, I'll just make one final point, which is that we have noticed in a paper in October that so normally symmetries can be either global symmetries or gauge symmetries, and they can either type of symmetry can have anomalies, but we think the gauge symmetries should have vanishing anomaly in order for it to be consistent. That works for the normal gauge and gravitational symmetries of the Standard Model. But some very great people have argued for rather compelling reasons, in my opinion, that Weil's symmetry, the local freedom to rescale the metric, should also be another kind of gauge symmetry. But it seems to have this trace anomaly, the trace T being non-vanishing, seems to indicate that it's an anomalous symmetry in the Standard Model. What we point out is that if you add a new kind of scalar field, dimensionless conformally coupled scalar fields, then this trace anomaly formula changes. It gets a correction depending on the number of these new dimensionless scalar fields, which I've denoted by n0 prime here. And also the vacuum energy, which is the bottom of these three equations, gets a correction in the presence of those fields. And actually, there's a unique now choice of the number of fields that causes both terms in the Weil anomaly and the vacuum energy to cancel to zero. And it turns out to match the Standard Model. It works only if the number of fermions is 4 times the number of gauge bosons, which is exactly true in the Standard Model. But it also works only if the number of ordinary scalars, n0, is 0, which indicates that apparently the Higgs field in this picture has to be not a fundamental field. It has to be some sort of composite field. And the last thing to say is just that these dimension 0 scalar fields automatically have a scale invariant spectrum, just like the perturbations we see in the early universe. So we think they provide a very promising new route to explain those perturbations without the need for intuition. And with that, I will thank you and turn it over to Neil, who will now explain how this picture gives a new way to compute the entropy, which gives a new explanation for the observed large-scale structure of the universe. Thank you very much.